Hello everyone, my name is Xinyang. I'm going to present our work, dense depth estimation from stereoendoscopy videos using unsupervised optical flow methods. Endoscopy is a tube-like camera with a lighting source on its end. It has varied applications such as stomach examination, sinus surgery, and appendectomy surgery. So why do we need to estimate the depth from endoscopy? With the depth information, we can register current frame to preoperative CT MRI navigation. Also, depth is the key component of 3D reconstruction, which can be acted as radiation frame examination. Lastly, depth is the key component in augmented reality. There are several ways to estimate depth. Structural light is the most accurate way, which is usually used to collect ground truth. However, it requires additional hardware and is sensitive to environments, making it hard to be incorporated in real surgery. Estimating depth from monocular endoscopy is the cheapest way, but also the most difficult way. Monocular endoscopy images suffer a lot from lighting changing and lose real scale. Estimating depth from stereoscopic images strikes the balance between structural light and monocular endoscopy. However, it's still challenging. Challenges associated with stereoendoscopy depth estimation are threefold. First, tissues have featureless surface, making it hard for traditional methods to find correspondences. Second, it's very difficult to obtain a large number of ground truths, so supervised methods are not good choices. Third, as endoscopy is often adjusted during intervention, accurate camera parameters are not generally available too, so methods depending on camera parameters are also not good choices. To solve previously mentioned challenges, we propose a supervised optical flow method to estimate the depth for stereo images. Here we first introduce the general routine to do unsupervised optical flow learning. An optical flow network predicts dense optical flows. We can use the predict optical flow to create warped target frame from source frames. The warped images should have similar appearance to the original frame. Based on this assumption, we can calculate the photometric loss between the warped images and the original images. As for another term, the smoothness loss, it encourages prediction to be smooth and propagate signal to textureless regions. Here is our proposed framework. We add a sparse flow loss to the framework. We use proxy label generated from SAFE to facilitate training. We use the auto-masking proposed from the previous depth estimation network to handle the situation where the photometric loss is not validated. In this work, we use the scarred dataset from MIUA challenge. It provides stereo images and the corresponding depth maps created from structural light. It was captured using a Da Vinci surgical robot on cadaver abdominal anatomy. For our results, we use mean absolute distance, absolute relative error, and the root mean squared error to evaluate performance. So the lower the values, the better the performance. We compared our method with traditional SGM method, unsupervised stereo matching method PASM, unsupervised depth estimation method mono depth 2, and unsupervised optical flow method A.I.L flow. We achieved the best performance according to our evaluation metrics. In ovation study, we show how each component gradually improves its performance. Sparse flow makes the largest contribution. We also compared our method with the Wiener method that utilizing ground truth. We achieve comparable results. Here we sample some images for visual comparison. Results from SGM tend to have some holes. Mono depth 2 have sharper boundary, but it loses real scale during our evaluation. PASM strongly relies on epipolar constraints, fails due to calibration issues. Our method predicts depths in real scale and has sharper boundaries than AR flow. We summarize our observation from experiments. Our method had the lowest errors among self-unsupervised method and has comparable performance to supervised method. In observation study, automasking helps remove errors where photometric loss is not validated. Sparse flow loss helps the network learn real-scale prediction. From visual comparison, SGM fails on featureless region. Monodepth 2 provides oversharp boundary. Airflow predicts blur boundary, and our method predicts reasonable boundary without losing real scale. In conclusion, back to the challenges. To overcome the first challenge, our method uses CN to extract features and use photometric loss to overcome featureless surface representations. To overcome the second challenge, we use self-supervised losses and proxy labels. To overcome the final challenge, we use an optical flow-based method that does not require camera parameters during training. Thanks very much for your listening. Appreciate great support from other team members of biomedical modeling, visualization, and image-guided navigation group, and our collaborators.